Hey everybody. Today we're going to be talking about diffraction. I moved this topic from optics into our modern physics unit because it can kind of go anywhere. So let's start with a definition of diffraction. So diffraction is um, essentially the bending of a wave when it encounters a barrier. So this can be seen with things like water waves and sound waves. We're going to focus a lot on light and some more electromagnetic type of waves, but really it can be seen with any type of wave. I'm going to draw a couple pictures here of what it looks like when there's diffraction happening through a little opening and also around a corner. So let's say we have some waves moving to the right, and we've got wave front. So think of this as like the crest of some waves. So if this was ocean waves, these would be like the top part, and then there would be a low part in between. So from the side, it would look like that. And so the wave is traveling to the right with some velocity. When it encounters this barrier, what happens is that it doesn't just keep going through in like a straight pattern like this. That doesn't happen. It actually bends outward in this sort of circular pattern. And that is what diffraction is. So that is through a little small opening. If we had the same sort of thing happening, we've got some waves. Imagine that those are straight up and down, and they hit this corner. They will also bend, um, but it'll look more like kind of just the part that hit that corner there starts to curve outwards. The rest of the wave keeps traveling in a straight pattern. Let me show you a couple pictures of this actually happening, so it's not my poor drawing. So here we have a little jetty here. This is a top view picture. We've got waves coming in. So the waves are moving kind of along to like kind of the top right corner. And then they hit this corner here, and you can see that these waves that hit that barrier bend in a circular pattern where these other waves remain is more of a straight pattern. And here's a picture of a large opening versus a smaller opening. So a large opening, only those waves near the edge will start to bend. The ones in the middle move in a straight line still until we get to the right kind of size opening here where we get this nice circular pattern. So we're going to be focusing on this sort of picture here where we want to have a small opening so that we get a nice kind of curved wavefront pattern rather than kind of this curve and straight pattern. And here's another couple of images, waves spreading out as they go through an opening and around an obstacle. So when does this happen? Okay. So specifically when I've got a small opening and the waves make that circular pattern, um, that will happen when the opening size, so that sort of gap there, um, is approximately the size of the wavelength. So, for example, sound has a wavelength of usually about 1 meter. So for sound to diffract, which we experience all the time, think about like the width of a door, that's about a meter. Um, you can hear someone speaking pretty clearly, even if you're around the corner. And that's because sound waves go through this 1 meter door opening here and kind of bend as they go through it. So if you're standing over here, you can still pretty clearly hear someone that's just on the other side of that open door. Radio waves, which have a much longer wavelength, up to like a kilometer, those can diffract around hills. So if we have hills that are even like a kilometer apart, radio waves can kind of diffract through that opening. Right, so then now why is this happening? I'm sure you're all wondering that. So the why is Huygens principle. So this principle states that if this is a wave front here, this wave front, which looks like it's a solid wave, you can think of this as like an ocean wave, the crest of it, let's say it's moving to the right. Huygens principle states that every single point on the wave acts as the source of a wave, or a source of a wavelet. Okay. So I'll write that out. Every point on a wavefront acts as a point source. So that means that every little point here acts like it's creating waves. So there's waves that are being generated by every single point on this wavefront. And these wavefronts are so close together, these little wavelets, that they constructively interfere to make a straight line. So there's really, really close together points that are all, excuse me, generating their own wave. And through constructive interference, they overlap in a way that make our wave fronts appear linear. So what happens is that if this wave with all these little wavelets come to an opening, so let's say I've got my wave coming up to this opening with all my little point sources of waves. If this little opening here is the size of a wavelength, essentially this one point here, which is generating new waves, generates waves through that opening that create this curved pattern, because now I've only got one little source of a wave, little point source here, creating new waves. So here, let me show you another picture of this. It's drawn a little bit better. So stated in another way here, we've got a wave here, wavefront A. These little points are little wavelets generating new waves. So this has some pretty crazy implications. Here again, we can see kind of these linear waves coming in, the little wavelets hitting this opening, generating new waves. And if the opening is wide enough, we still get that straight sort of pattern, but then the outsides curve. So let's talk about Young's double slit experiment, because this kind of combined with Huygens' principle has some crazy implications for physics. So Young's double slit experiment, what he did was he cut two slits in a card. So this here is a card that has two slits in it. And then he shined some sort of monochromatic, so that's just one color, light. So it's a little flashlight there at the card. And if light coming at this card, if light was acted like a particle, which we'll talk about more tomorrow, if it acts like a particle, so we have like little particles of light, we would expect that them to hit this screen over here and just create a bright spot here and a bright spot down here. That is not what was seen. So let me erase this all real quick. So here we've got light coming in. And if light is a wave, light comes in, and if these slits are small enough, they'll diffract through these two openings. And what happens is if these are crests, where the blue lines that I'm drawing, and then there's little like troughs in between, what ends up happening is that on the screen over here, we end up with patterns of bright spots and dark spots. And that's what Young actually saw. So in the middle here, if I kept drawing these wave fronts on the screen, he saw a really, really bright spot in the middle. And then he saw other bright spots at different locations. So these are all bright spots here. And then in the middle, he saw dim areas. So if I'm looking from the side here, we would see a bright spot and then other spots that got a little bit dimmer as they go to the right, but they're still bright spots with dark spots in between. So I could think about this if I did like the intensity graph here. I would have bright, brighter, brightest, and then kind of a mirror image on the other side. So what's happening again is that these waves of light are constructively interfering to create a bright spot and destructively interfering to create a dim spot. So importance. This experiment proved that light acts like a wave. So super, super cool. We've already known that light acts like a wave, but this experiment proved that. And here's another picture. We've got light wave coming in, then it diffracts through two openings, and then we get on the screen a bright spot. So that's going to be called a maxima, and then a dim spot, which is a minima. All right, let's go through the geometry behind this experiment because we do have a couple of equations to go along. So this distance right here between the slits is d. That's our distance between the slits. And then we've got a little angle in here, theta. And then this difference, so if I have a distance measured to, let's say this is our first, this is like the central fringe, and this is the next brightest one. The difference in those measurements right here is going to be approximated with m lambda. M is going to be the number of bright spots away from the central bright spot that you are. So this would be m equals 0. That's our central. They're called fringes. This would be m equals 1, and then m equals 2, and then it's mirrored on the other side. So it's just looking from the center, how many bright spots away are you? So to figure out some, according to like the distance between the slits and then what bright fringe we are away, we can do a little trig here. From this angle, we can say that sine theta equals opposite, which is m lambda over d. And there are some like assumptions that we're making here, but for the most part, this is a good approximation. All right, and then if we want to figure out the distance from our card to the screen. So this distance is distance L. Given this central angle here, which we are approximating again, actually measuring it from one of the slits, but we can approximate because this is a very small distance here. And then this distance, y, again, from the central fringe to the outside. We can use a little trig again. This will be a tangent angle. So tangent theta equals y over L. This is usually written as a y equals equation. So y equals L times the tangent of theta. So let's do an example. We have two slits that are separated by 8.5 times 10 to the negative 5 meters. The screen, so that L distance is 2.3 meters. And the 10th bright fringe, so that means M equals 10, is 12 centimeters above the central bright fringe. So that Y distance is 0.12 meters. So first, let's figure out what that angle is between that central bright fringe and that 10th bright fringe. So we know this distance is 0.12. We know this distance is 2.3 meters. So this angle here is going to be the inverse tangent of 0.12 over 2.3, which is 3 degrees. Then we can use our other equation, which is that the sine of theta equals m lambda over d. We're trying to figure out lambda, so let's rearrange this into d sine theta over m. So 8.5 times 10 to the negative 5 times the sine of 3 degrees divided by 10, because that's how the number of bright fringes away we are. And that comes out to 4.4 times 10 to the negative 7, or 440 times 10 to the negative 9, which is 440 nanometers. 440 nanometers is in the blue range. So this would be blue light. Right? Thanks a lot.